Hello guys, welcome to another video in our YouTube channel. So in this video we are going to be analyzing a car carriage system moving up an inclined slope. So we have a equation in front of us. I'm just going to read the equation and I'll kind of do the brief analysis of the equation while you look for your final answers. Alright, so the equation reads: a car of mass 10,000 kg pulls a carriage of mass 1,000 kg up a rough hill inclined at sine inverse of 3 feet. There is a total known gravitational resistance of 500 newtons, and this is divided between the car and the carriage in the ratio of their masses. The coefficient of friction of the rough hill is 0.15, and the engine of the car produces a constant pull, and the carriage accelerates from a speed of 4 meters per second to 10 meters per second in a distance of 14 meters. Find the magnitude of the tension in the tow rope and the tractive force of the engine of the car. So in situations like this, the first thing you do is that you draw your diagram, alright, indicating all the forces acting on the various bodies. Then you apply the Newton's second law of motion in a given direction. Then you find what you have been asked to find. Okay, so let's go ahead to draw a diagram. So the first thing I have an inclined slope. Okay, so I have an inclined hill. So here I consider this to be my horizontal, and then this is my inclined hill. Now this inclined hill is at an angle of, I'm just going to call that angle theta. Okay, that angle is theta to the horizontal, and we know that theta is actually sine inverse of 3 divided by 5. So like I said, I'm just kind of doing a brief analysis. At the end I'll come out with general formulae where you just have to replace the respective values given to get your final answer. So that's the angle that the rough hill makes with the horizontal. Now I'm just going to indicate my carriage. Okay, so this is my carriage, and then we have the car. So here's my carriage, then we have a car, and the car is pulling this carriage up this inclined slope. So we have a car, so the first thing we'll have to do is okay, so here we have a car. Now let me try to, now we have a rope that is connecting the car. We have a rope that is connecting the car to the carriage. Alright, that's a tow rope, so there is tension in the rope. So we are going to indicate the various forces that are acting on both of them. So first of all, we have tension. Since this rope is attached to both the car and the carriage, then the tensional force is acting towards the car, and also the same tensional force is acting towards the carriage. So you should take note. That's Newton's that law. So on this rope here we have a tensional force of T that is acting in opposite direction. So the tensional force is T. That tensional force is both acting towards the car and also towards the carriage. So I have the tensional force here, and I also have the tensional force here. Okay, we call it T. Now the next force that is acting on the car is the tractive force, the force that is taking the car upwards. Okay, and this force is actually produced by the engine of the car. So we are just going to call that force F. Alright, so we have the tractive force. Let me just call it F. So that is F. Now which other force is acting on the car? We have First of all, we have the weight. Okay, the weight has a vertical and a perpendicular component. Anyways, let me talk about the carriage. So for the carriage, we have the frictional force, because the slope is rough. We have the frictional force here for the carriage, and this frictional force, I'm just going to call it maybe F friction 1. Okay, that is for the carriage, because the car also has a frictional force. So we have F friction 1. All right, now also we have the weight. The weight is acting vertically downwards. Okay, the weight is acting vertically downward, and you should know that this weight has both a component that is actually this weight has a component that is parallel to the plane, all right, that is in the same direction of the plane, and it has a component that is perpendicular to the plane. So the weight is mg, but I'm just going to call it small m, and you should know that small m is for the car, is for the carriage, sorry, so that when you're replacing your values, you should know. So the weight is mg. This small m is a mass of the carriage, so that's my weight, mg. Now this weight has a component that is perpendicular to the plane. This is a component here. All right, I'm going to put this component in this coloration. I'm going to put it in red. That's a component, and by resolution it gives us mg cos theta. Okay, it gives us mg cos theta. So that's the component. Now it also has a component that is parallel, which is now mg sin theta. There's a component that is parallel to the plane. This is a component here, mg sin theta. All right, now according to the equation, now this guy here is what we call the normal reaction. Okay, the normal reaction of the carriage. I can call it R1. You should know that R1 is a normal reaction of the carriage. Okay, I'm going to call it R1. Now let us also go to the car and also indicate all these forces. So here in the car, we also have the frictional force. We can call it FR2. That's the frictional force of the car. Now let's indicate the direction. The frictional force is also acting downwards, is opposing the motion because the motion is upwards. So we have the frictional force FR2 for the car. Now aside this frictional force, we also have the perpendicular component of the weight. Okay, now we also have the parallel component of the weight. We have the perpendicular component of the weight, and we have the parallel component of the weight. Then later on we have the weight itself. Okay, so for the car, I'm going to call the mass of the car capital M. All right, so for the perpendicular component of the weight is going to be capital mg cos theta. So this capital M, the angle is the same. Okay, now for the parallel component is going to be capital mg sin theta. All right, that's a parallel component. I'll just try to decrease the size so that at least it should enter here. So in questions like this, the first thing that you do is you indicate all the forces. So this is mg sin theta. Okay, that is mg sin theta. Now the next thing to do is we also have to put the normal reaction force for the car. The normal reaction force is in the same direction as the perpendicular component of the weight. That normal reaction force, we are going to call it R2. Okay, all of these things, all of these forces I'm indicating are going to be useful. So the question is too broad, too broad, and if you make a mistake, it becomes a very big problem. All right, now there is also something. All right, in fact, let me indicate this weight here, because because you also have the weight, though we don't actually need it, we need just the components, but let me just indicate it. All right, let me just indicate it. So the weight is actually capital mg. All right, capital M times g, since we are dealing with a car. Okay, now there's one last force that we have to indicate, I think. So the mass is capital M for the car, and for the carriage is small m. The angle is theta, which is sine inverse of 3 divided by 5. Now we have not indicated the known gravitational resistance of 500 newtons, but now this known gravitational resistance of 500 newtons is actually divided between the car and the carriage in the ratio of their masses. So we are going to find the resistance of the carriage and the resistance of the car. So let's do that. So total known gravitational resistance is equal to 500 newtons, but it is divided in the ratio of the masses, and according to the equation, they said is divided is divided between the car and the carriage in the ratio of their masses. So we are going to have the car first. The mass of the car is to the mass of the carriage. That is the ratio. All right, so if we want to find basically the resistance, the non-gravitational resistance of the car, of the carriage, I'm going to call it arrow carriage. Okay, now what do? We take the ratio, we take the mass of the carriage divided by the total ratio, right? We take ratio of the mass of carriage divided by sum of ratios, okay, then times the value of 500 newtons. I believe this one is even back then in primary school, where we take the proportion given to you divided by sum of ratios, then times the final amount. All right, so I'm just going to look for the value. Okay, so this is 1000 divided by, what is the sum of ratios? It's 10,000 plus 1000, that is 11,000. Then we multiply it by 5,000 newtons. We are going to get the resistance of the carriage. All right, now to find the resistance of the car, we just have to take the total resistance minus the resistance of the carriage, or you actually take the mass of the car divided by the sum of the ratios times 500. If you do any of them, you're going to have the same answer. In other words, we are saying that you take 10,000 divided by 11,000 times 500 newtons. You're going to have your answer. All right, so we now have to come back to our diagram, and then we indicate that resistance, that non-gravitational resistance. Okay, we have to indicate it. So for this guy, for the carriage, I'm going to call it arrow carriage. Okay, and it's actually in the direction of motion. All right, it's in the direction of the slope. So we call it arrow carriage. Like I said, let me just try to decrease the size so that at least it can be placed here. So arrow carriage. Okay, you have the value of arrow carriage. Now we also have to indicate for the car, arrow car. Now there is no space, so I don't know where I'm going to put it there. Anyways, let me just try to create space up here. Let me just shift away these tensions first, then I try to create space up here and put it. All right, so that is it. Voila. So I'm just going to put it there, and we are going to call it arrow car. We call it arrow car. So that is arrow car. Okay, Now I think with this we have actually completed the force diagram for the whole system. Now all we need to do is we apply Newton's law of motion, second law, precisely along the inclined slope, because we have to apply the law in a given direction. All right, so the direction of motion, let me indicate the direction of motion. The car is pulling the carriage up the inclined slope. The car is pulling the carriage up the inclined slope. So this is the direction of motion, up the inclined slope. That is actually the direction of the acceleration. Okay, so I think with this we are now good to go. Okay, now we have to apply Newton's second law of motion along the inclined slope. So applying Newton's second law of motion along the slope. Okay, now we actually have to apply it with regards to the whole system and also with regards to the carriage. All right, so take note. So firstly, let me talk about the whole system. That is the car carriage system. The car carriage system. Now this Newton's law says that the net force acting in a system is equal to the mass times the acceleration of that system. That is basically what it is saying. All right, and the net force is basically the force that is taking it along that direction minus the resistive forces. All right, so if I want to consider for the whole system, I'm going to take all the forces that are pointing upwards minus all the forces that are pointing downwards to be equal to the mass times the acceleration. Let us even calculate the acceleration before. All right, let us find acceleration. So acceleration, you should take note that the acceleration of the system is the same as the acceleration of the carriage, and we're being told that this carriage accelerates from a speed of 4 meters per second to 10 meters per second over a distance of 14 meters. So we can use, since the inclined slope is actually a straight line, all right, it's a straight line, so we can use the Newton's law of uniformly accelerated motion, that is motion in a straight line. Now we have initial speed, we have final speed, and we have distance. How do I find acceleration? So I just need to use a formula that there is no time inside. So v squared is equal to u squared plus 2as. All right, so from here we can realize that 2as is v squared minus u squared. Now I think we can now easily find the acceleration by dividing both sides by the distance. So my acceleration of my system is v squared minus u squared divided by 2s. We have v, we have u. Your v is 10 meters per second, your u is 4 meters per second, and your s is 14 meters. So you will be the one to find the value. All right, so I'm just going to input the values, you punch and have your answer. So this is 100 squared, so sorry, this is 10 squared minus 4 squared divided by 2 times 14. You will get your answer of the acceleration. Okay, now let me take you guys to the next page. So we are going to use Newton's second law of motion along the inclined slope. All right, so let me just apply it here before we go down. So if we take it along the inclined slope, okay, that is for the whole system, which force is taking the system upwards? In fact, all the forces pointing along the slope in the positive direction of the slope. All right, that is all the forces pointing up the slope minus all the forces pointing down the slope is equal to the mass of the whole system times the acceleration of the whole system. So the first force pointing up is the attractive force of the car, which is F. Now the next force that is pointing up is a tensional force. This first tensional force, we call it T. All right, now is there another force pointing up? No, there is no other force pointing it up. Now which forces are we subtracting? We are subtracting, first of all, since I'm dealing with the whole system, let me begin with the carriage. I'm subtracting arrow carriage. Since I've already put this minus sign here, I'm just going to sum all the forces pointing downwards. Okay, so this is basically the sum of all the forces pointing upwards, then minus the sum of all the forces pointing downward. So we have arrow carriage, we have arrow car, we are done with the non-gravitational resistance. Now which other force is pointing down? We also have this tensional force here, okay, that is pointing down. We have T. Which other force is pointing down? We have the component of the weight for the carriage along the slope, so it is small mg sine theta. We also have this component of the weight of the car pointing down the slope, which is mg sine theta, big mg sine theta. Okay, then let's go to the frictional forces. We have F friction 1 plus F friction 2. F friction 1 plus F friction 2. Okay, that's what we have. I think we are done. Then now we have to equate this to the mass of the whole system, which is the mass of the carriage plus the mass of the car, which is 11,000, then times the acceleration. All right, then times the acceleration. Now there is something we also have to find. Now, do we know F? We don't know F. Do we know T? In fact, let us just simplify and you see what happens. So if I expand, I'm going to have F. Now this T here we cancel with this T here, so T goes away. All right, so we have F here minus arrow carriage, okay, minus mg sine theta, okay, minus mg sine theta, then minus f arrow 1 minus f arrow 2. Oh, I forgot to subtract arrow car minus arrow car first here. If I subtract here at the last, I'm still correct. Then equal to small m plus capital M times the acceleration. So from this, let's look at what we have. We have arrow carriage, okay, we have arrow car, okay, we have mg sine theta. We know that theta is sine inverse of 3 on 5, so sine theta is just 3 divided by 5. All right, so let me write down informations. If theta is equal to sine inverse of 3 divided by 5, what does it mean? It means that sine theta, take sine on both sides, is equal to 3 divided by 5. Now what about cos theta? Cos theta, remember we know that cos theta is the square root of 1 minus sine squared theta, because cos squared theta plus sine squared theta is 1. So this is cos theta. This angle is an acute angle, so we take the positive square root. So we are going to have the square root of 1 minus, if I square 3 on 5, I will have 9 over 25, and if I subtract, I'm going to have 16 on 25. Okay, and 16 on 25, the square root is 4 divided by 5. So the value of cos theta is 4 divided by 5, and the value of sine theta is 3 divided by 5. Now automatically we are also going to know this man, all right, because we know capital M, we know G. We are going to take G to be 10 meters per second squared, because we are dealing with mathematics with mechanics. If we are dealing with physics, most of the times G is 9.8 meters per second squared. Now you realize that we know small m, we know capital M, and we know the acceleration as well. Like I told you, you'll be the one to punch and have your answer for the acceleration. Arrow carriage and arrow car, you know them. All right, in fact, if we sum arrow carriage, if we take arrow carriage plus arrow car, you have 500. So you can just replace this man here with 500, or you can also replace it and replace it here. When you subtract the two, you still get negative 500 because you're subtracting. Okay, now what is left? We need frictional force 1 and frictional force 2. We need them. Now, since the body is not moving perpendicular to the inclined slope, it means that the forces along the perpendicular are balanced. So if I take the car, I'll have r2 is equal to mg cos theta. If I take the carriage, I will have r1 is equal to mg sin theta. Okay, I want us to take note of that. So for the car, we have r2 is equal to mg cos theta. Okay, why am I using this? It is because by definition the frictional force 2, okay, the frictional force is always equal to the coefficient of friction times the reaction force. All right, the coefficient of friction was given to us in the equation as 0.15. r2 is equal to what? Mg cos theta, which means that this man is just 0.15 times capital Mg cos theta. Do we know cos theta? Yes, we know cos theta. Cos theta is 4 divided by 5. So you do this to find Fr2. Okay, now let's talk about the carriage. Okay, let's talk about the carriage and also find the frictional force. So for the carriage, we know that R1 is equal to small mg cos theta. Alright, which means that my Fr1 will just be equal to, it is still mu because they are on the same plane, so the same coefficient of friction applies. It is a constant. So my mu is equal to this times R1, which is 0.15 times small mg cos theta. Do we know small m? Yes, we know. Do we know cos theta? Yes, we know. It's 4 divided by 5. So with this, you're going to find F2. So at the end of the day, we have everything here. And if we have everything here, what is going to be the attractive force, which is F? Our F will just be equal to this guy here plus all of this. So we just add these guys on both sides. We are going to get our attractive force. Alright. So this is not supposed to be here. I'll just take it down to the whole system. Alright, so like we said, we're analyzing for the whole system. This is what we have. Okay, and from there, the attractive force, capital F, let's just find it. So capital F will just be equal to small m plus m times A, then plus everything here, because we have to add these guys on both sides of the equation. So all these minus signs becomes plus. This man is plus. This man is plus. Frictional force 1 is plus, and this guy is also plus. Now the second thing we have to do is that we have to find the tension in the tow bar. All right. So for us to find the tension in the tow bar, we are going to consider only the carriage. All right, if I consider only the carriage, now we are also going to apply Newton's second law of motion along the inclined slope just for the carriage. Now just for the carriage, the force that is pulling it up is actually T. Okay, that is the only force taking it up. Now what are the resistive forces? Minus mg sin theta, then minus again arrow carriage, and then minus F R1. Voila, I think we have this force. We have three resistive forces. We have the component of the weight along the plane, we have the non-gravitational resistance for the carriage, and we have the frictional force. Then we have to equate it just to the mass of the carriage times the acceleration. Alright, so from here we are going to get directly the tension, which is going to give me MA plus mg sin theta plus arrow carriage, then plus F arrow 1. Do we know M? Do we know A? Yes, we do. Do we know mg sin theta? Yes, we do. Do we know arrow carriage? Yes, we do. Do we know F arrow 1? Yes, we do. From there, we are going to have the tensional force in the tow rope. Alright. So I think what you are now supposed to do is you just have to basically look for the final answers and the question is done. Alright, thank you guys for watching and see you guys in the next video. If you love the video, make sure you like the video, share the video with your friends, and you also subscribe to the channel. If you have some difficulties, make sure you indicate those difficulties in the comment section of this channel and I'll be glad to respond to you. Alright, until the next video, stay blessed.